In today's video, we're going to be talking about matter. After watching this video, you should be able to describe the subatomic particles of the nucleus, understand the nuclei numbering scheme that was used in physics. It's a little different than what you've probably have learned in chemistry. And then we're going to introduce a new force, and probably the last force. It's going to be called the strong force. So here we go. Just a refresher, atoms are made up of protons and neutrons and electrons. Okay, so protons and neutrons are found in the nucleus, and they are typically referred to as nucleons because they are found in the nucleus. So protons, neutrons found in the nucleus, and that nucleus is then surrounded by electrons that are orbiting around that central nucleus. And just a refresher from static electricity, protons are positive, neutrons carry a neutral charge, and electrons have a negative charge. So let's get into talking about mass and charge of protons, neutrons, and electrons. The atomic number, which is referred to as the letter Z in physics, is the number of protons that you will find in the nucleus. And in terms of mass, protons and neutrons are quite a bit more massive than electrons. They're about 1,800 times more massive than electrons, so pretty incredible. The atomic mass unit, which is referred to as U, is equivalent to 1.66 times 10 to the negative 27th kilograms. So a super small number. So typically, even though kilograms is like the standard unit to use when you're measuring mass, for this unit we typically will use the atomic mass unit, which is equivalent to 1.66 times 10 to the negative 27th kilograms, but who really wants to say that or write that over and over again? So we just call it one atomic mass unit. In terms of describing nuclei, over here on the left-hand side, we have a helium, right? He stands for helium, and we've got this numbering scheme here. Here's a 2 and here's a 4. Those numbers mean something, and this is just an example of just any old element. X is just any old element. There isn't an element X on the periodic table yet. Who knows? Maybe there's one to be discovered. And then this letter Z here is the atomic number. It's the number of protons. Also, sometimes it's looked at as the charge on the nucleus. What kind of charge does the nucleus have? And when you're talking about charge, you're talking about E elementary charge. Okay, so if you remember back to static electricity, a proton has 1 elementary charge, if you will. So this number here, in terms of helium, this 2 means that it has 2 protons, or it has a plus 2 elementary charge. Okay, it has a positive 2 charge. That nucleus has a positive 2 charge. The A up here is the mass number. Again, the unit is the atomic mass unit, and basically that is the number of protons plus the number of neutrons. Okay, and that number is up here, which I know in chemistry I believe it's flipped the other way around. You know that the atomic number is on top and the atomic mass number is on the bottom. In physics they do it this way. Don't ask me why, but this is kind of the way things are. So just kind of keep that in mind. The bottom number is the atomic number, the top number is the atomic mass number, and the atomic mass number, if you look at the periodic table, it is actually an average mass number for whatever element you're talking about. So it looks at all the isotopes that an element has and takes an average of the most common mass, and that's why you always have like these decimal points, or a decimal point with all these little numbers after it, is because basically you're averaging the isotopes of that element, which we haven't talked about isotopes yet, but that's actually the next slide, so we'll get into that in just a second. But just kind of keep the schematics in mind in terms of like this little symbol here means the element you're talking about. So in this case it's helium. The number down here is the atomic number, and the number up here is the atomic mass number. Okay, let's talk a little bit about isotopes. Basically, an isotope is an atom that has the same number of protons, because the number of protons actually dictates what atom you have, but it has a different number of neutrons. So I give you an example here. Hydrogen, believe it or not, has 3 isotopes. I kind of look at it as like twins or what have you. Okay, that hydrogen isotope, all those hydrogen isotopes, I should say, always have 1 proton. And they also have 1 electron. What varies between the three different versions of hydrogen is the number of neutrons in each of those hydrogens. So here you can see one type of hydrogen is called protium, another one is called deuterium, and the third one's called tritium. And basically they vary in terms of the number of neutrons that each of them has, and that's an isotope in a nutshell. Okay, let's introduce this new force. It is called the strong force. And you may be saying to yourself, okay, I know the nucleus contains positively charged protons and neutrally charged neutrons, right? The question should arise in your head, how do those protons stay together? Because they're positively charged. And we learned back in static electricity that like charges repel each other. Okay, so those protons have no interest in actually staying together in that nucleus. So there must be some force that's holding them together, and this is where we come with our new force. It is called the strong force. The strong force, as the name implies, is actually extremely strong. It's strong enough to overcome the electrostatic force that the positively charged protons are exhibiting upon each other. The caveat or the catches to the strong force is that it acts at very, very short distances. I mean, we're talking, super small distances. So if those protons get a little too far apart from each other, the strong force loses its ability to hold them together, and then boom, they separate, they spread apart because like charges repel. Okay, and this actually is what happens in terms of like radioactive decay. Basically, the nucleus itself becomes unstable and things start shooting out of the nucleus. And we'll get into that later, but basically the strong force has been overcome and the electrostatic force takes over. Okay, that takes care of this video. I will see you guys next time.